Hi everyone, in this video we're going to go over Taylor series and Maclaurin series. When we were doing power representation of geometric series to create representation for other functions, then we find out that we could make derivatives of the functions and that we could make in turn derivatives of the power series term to term. And so what's that going to produce is that if I have a function that can be represented as a power series, that's going to have a certain radius of convergency and an interval of convergency. And that interval of convergency and radius of convergency is going to be mostly inherited by the derivative of the function and the power series derivative. Now, another thing that happens is that you're going to be able to find certain values of the coefficient and relate them to values of the derivative. So for example, if f of x is this power series, clearly when I plug in a here, this is going to make 0 most of the terms. And so we're going to have that f of a is just going to be the first term a0. Now if we do the first derivative, then now my new first term is going to be the term a1, and when I plug in a for f prime, I'm going to have that f prime of a is a1. If I continue doing that, I'm going to find out that for f2 prime, I'm going to find f2 prime of a is 2a, and in general, if I just continue finding the derivative values of a, I'm going to find out that the value of the n derivative at a for this function is going to be given by n factorial times the term a to the n of the sequence. Now, if we solve for the n coefficient of the series, then we're going to get that essentially the n coefficient of the series can be seen as the n derivative at a over n factorial. And so just this representation, it gives me a completely new form of taking a function and representing it as a power series. Because remember, just a power series is essentially just a group of coefficients and power of x minus the point where it's going to be centered to the n. So the real important thing is, how am I going to find an? Well, this power series representation and the idea that I can take the derivatives leads me to find a representation for that sequence of coefficients. Now, this can be synthesized in a theorem, and in general, if S has a power series representation at x equals a, so if f of x can be seen as the series from n equals 0 to infinity of an x minus a to the n, when the absolute value of x minus a is less than a certain number r, then the coefficients are going to be given by the formula an equals to the n derivative of f at a divided by n factorial. Now this series is going to be called the Taylor series of the function at a. In the particular case when a is equals 0, then it will be called a Maclaurin series. Okay, so Taylor series and Maclaurin series, they're essentially the same thing. It's just that Taylor series is for a series that is centered in a point that is no 0, and Maclaurin is specifically talking about when we're centering around 0, which is the most common case that you will see. Now let's see some examples of finding Maclaurin series for a couple of functions. Alright, for the first function, we're going to find the Maclaurin series for the function f of x equals e to the x, and then we're going to proceed with all the other functions that we have in there. So let's consider f of x equals e to the x. Now, e to the x has a particular relationship with the derivatives, and it's because they're going to be the same. So f prime of x is e to the x, f2 prime of x is going to still be e to the x, and in general, the n derivative of x is going to be e to the x. Remember that we're talking about getting a Maclaurin series, so this means that we're always going to get around 0. So we care about what is f of 0, we care about what is f prime of 0, f2 prime of 0, and fn of 0. So in this case, it's easy because since it's always the same function, e to the 0 is just 1. And so if I'm trying to get the sequence an equals af n derivative at 0 over n factorial, then this is going to be simply 1 over n factorial. And I'm done. And so it's a very simple example. The power series representation here is e to the x is the series from n equals 0 to infinity of x to the n over n factorial. And that's it. This is the power series representation that we get by doing this derivative. Now, things are not so easy on other scenarios. So sometimes you're gonna have to do a little bit of sequencing to find the actual coefficients, and so that's one of the cases here. For example, on the next scenario, we're gonna have b f of x is just gonna be 1 plus x power to the k. Now the first derivative here is just gonna be k 1 plus k to the k minus 1. The second derivative is going to be k times k minus 1 to the 1 plus k minus 2. And the third derivative is now k minus 1, k minus 2, 1 plus x to the k minus 3, and so on and so forth. So if we continue going here, we can see that the nth derivative is just going to be the multiplication here of k minus 1 up to, and because we're doing n derivative, this is going to be k minus n plus 1, 1 plus x k minus n. And so now, if we're actually going to plug in 0 and find numbers, then notice that we find very different things. So f of 0 is just going to give me 1. F prime of 0 is now going to give me k. F 2 prime at 0 is just going to give me k times k minus 1. And you can see how it goes. In general, it's going to give me the coefficients that I have here in front of this 1 plus x k minus n. So fn of x at 0, sorry, is going to be k times k minus 1 times k minus n plus 1. And so you can see that this is kind of the way that the coefficients are going to be working on. And so this is the n coefficient really. So when I get the an term, this is k times k minus 1 times k minus n plus 1. Now getting this sequence is kind of difficult sometimes. And this is an area, there was a very particular form that it was developing, but sometimes you gotta find out what type of shape this is taking, and that's when it might become very difficult. This is an area we simply just are going to write 1 plus x to the k, or the binomial to the k, can be seen as the series from n equals 0 to infinity of k minus 1 times k minus n plus 1 over n factorial x to the n. Okay, this is just a representation of what we are used to call the binomial series. Okay, in general, notice that this arrangement that we have over here, k minus 1 times k minus n plus 1, can actually be represented with the binomial k choose n, and so that's gonna help me out see that as this representation. Okay. Now, last but not least, a trigonometric function. So we have f of x being cosine of x. And make sure that you look at the practice videos, because we're going to have much more examples in there. So just make sure that you're taking a look at those. So if I have f of x equals cosine of x, one of the things that you'll see is that f prime is going to be minus sine, since that's the derivative of cosine, minus sine. But when you take another derivative, then you're going to have that this is minus cosine. So you cannot return to the original function, but now it has a negative sign. So you cannot see where I'm going with this. Now f of 3 is going to be now sine again, positive, and then f to the 4 is going to be cosine of x, and then f to the 5 is going to be back to being sine. See? And then again minus cosine. Okay? And so now at that point, then we plug at 0. And so here's some things are going to happen. So notice when I plug at 0, everything that is a sine is going to become 0. So this is just f of 0 is going to be 1, but f prime of 0 is going to be 0. f2 prime of 0 is going to be minus 1. f3 is going to be 0 again. Now f to the 4th is going to be 1 again. F to the 5 is going to be 0. And f to the 6 is going to be minus 1. So notice that it doesn't make sense for me to actually just pay attention to the zeros. Instead of that, I should be taking a look at what is surviving. Notice that it survives when n equals 0. It survives when n is equals 2. It survives with n is equals 4. And it survives when n is equals 6. And this is jumping from minus 1 to 1. So this is something that you can just see as minus 1 to the n, right? So the coefficients that you're going to find out is that an is just minus 1 to the n, because that's jumping from 1 to minus 1, from 1 to minus 1. But then, instead of being over n factorial, because the only thing is surviving is the odd, is the even members. So instead of just doing n factorial, I'm just going to do 2n factorial, because it's the only members that are going to survive: 0, 2, 4, 6. So it only makes sense to write those out. Okay, so this is the fn at 0 over n factorial, or k factorial. Let me call this with k, so it kind of makes sense. Then I'm changing the index, k factorial, but this k is really 2n, because those are the ones that survive. And so what this tells me is that now cosine of x can be represented as the series from n equals 0 to infinity of minus 1 to the n, x to the 2n's is only the even members are surviving, over 2n factorial. And that concludes some examples of representation of Maclaurin series.